Let us try to understand and analyze buck converter circuit or step down converter circuit. In this converter circuit we have two switches S1 and S2 and one inductor L and one capacitor C. The output voltage is the voltage across the capacitor C. That is why a load resistance, a resistance which represents the load, is connected across this capacitor, and V in is the source. And what are we given? We are given the states or the state combinations. Obviously S1 and S2 cannot be on together because we will be shorting a voltage source, so they have to be alternately conducting. So S1 on, S2 off is one state, S2 on, S1 off is another state, and so on. Of course, the state of both being off is also possible, in which case the inductor current will be 0, and that state exists in something called discontinuous conduction mode of operation. So we are not considering the discontinuous conduction mode here. We are interested to look at the continuous conduction mode. That means the inductor current IL is always positive, so it has to be flowing through S1 or S2 at any given point of time. So we are given the state combinations S1 on, S2 off for some time. And how much is the time? It is dTs. It is dTs, a fraction of one period Ts. And for the remaining time, which is 1 minus dTs, the other combination is there. So S2 on, S1 off, and these two combinations repeat. So for dTs, S1 is on, and for 1 minus dTs, S2 is on in every interval of Ts. This D is known as duty ratio, which is a very popular term used in DC to DC converters. The first step is to draw converter circuit in the corresponding states. So when S1 is on and S2 is off, that means from 0 less than t less than dTs, in that interval the circuit looks like this. So S1 is on, so it is represented as short circuit. S2 is off, so it is open circuited. Rest all elements are intact. Similarly, from dTs to Ts, for dTs less than t less than Ts, in the second interval, which is of duration 1 minus d times Ts, S1 is off, S2 is on. So S1 is represented as open circuit, S2 is represented as short circuit. That is shown here. Once we have written the circuits, next is to look at what do we want to know. We want to know the average output voltage, average value of the output voltage VO of this converter. That is our interest, because that is what is getting applied to our load. Since we are interested in voltage, it is better to write KVL equation. And if you write KVL equation in both intervals, like in the first interval, VL is equal to V in minus VO. In the second interval, VL is equal to minus VO. And what do we do next? We apply our approximation. What is that? That is the small ripple approximation. We intend to produce a constant DC output voltage ideally, but we will end up producing some kind of variable output voltage. However, the variation is assumed to be negligible. That means the output voltage is approximated to its average value, and we are denoting the average value of output voltage VO average by simply VO, capital VO, for ease of analysis. And what do you mean if you look at the waveform of output voltage? For example, let us say if your output voltage has this kind of waveform as shown here, it will have some ripple, this delta VO, peak to peak ripple, and the average value is VO. So the approximation will be delta VO is much smaller than VO. So we are taking an approximation and proceeding with the analysis. So we need to make sure that this approximation holds good. That means we need to make sure that this delta VO is much smaller than VO under all circumstances. And how do we make sure that it will happen? By choosing an appropriate value of capacitance. So we'll also see how to choose an appropriate value of capacitance so that this approximation is valid, so that our analysis becomes valid. The next step is to apply the principles of periodic steady state. We know that in periodic steady state, the average voltage across an inductor is 0. So if you apply that, it will be 1 by Ts integral 0 to Ts, because our time period is Ts, because that things are getting repeated over every Ts. The states are getting repeated over every Ts. So 1 by Ts integral 0 to Ts, VL dt will be 0, and with our small ripple approximation, the expressions for VL in both intervals are V in minus VO and minus VO, where VO is constant. So we can simply multiply by the intervals and evaluate the integral. So it is V in minus VO times dTs plus minus VO times 1 minus d times Ts is equal to 0, which will directly give us the result VO is equal to d times V in. Obviously d can be less than 1, d is between 0 and 1, so the average output voltage is definitely less than the input voltage. The waveform of inductor voltage VL is also shown here, where the value of VL is V in minus VO for a duration of dTs, and that is a constant value, almost a constant value with our small ripple approximation, and it is minus VO for the remaining time in a duration of Ts, that is 1 minus d times Ts. And the areas that are marked under the positive and negative portions of VL are equal. That means volt second balance is maintained and the average voltage across inductor is 0. Remember, we have only obtained the average value of output voltage. We have not yet obtained the waveform of output voltage. And how do we obtain the waveform of output voltage? It can be obtained by integrating the current through the capacitor, because the output voltage is nothing but the voltage across the capacitor, which is the integral of current through the capacitor. And how do we obtain the current through the capacitor? For that, we need to apply KCL at this node. And if you apply KCL at node A, it is going to give you IL is equal to IC plus IO. And what is IO? IO is nothing but VO by R. And with our small ripple approximation, IL becomes equal to IC plus capital VO by R. Capital VO is the average output voltage, and the capacitor current, which is of interest to us because we want to look at the output voltage waveform, will be given by IL minus VO by R. If you want to look at the capacitor current, you need to look at the inductor current and subtract VO by R from the inductor current. So let us take a look at the inductor current waveform now, and from there we will deduce the capacitor current waveform. How will the inductor current waveform look like? In the first interval, the voltage across inductor is positive. That means di by dt is positive. That means the current through the inductor is rising, and also since the voltage is constant, almost constant, the current through the inductor should rise linearly. But where will it start? Let us say in periodic steady state it will start at one point. So the inductor current rises linearly like this. And what is the slope? The slope of this line, the red color line that we have drawn now, is V in minus VO divided by L, the value of L. That is the slope of this line. And in the remaining interval 1 minus dTs, the current is going to fall. Why? Because the voltage across inductor is negative, so di by dt is negative, so the current is going to fall. And how will it fall? It will again fall linearly because the voltage across inductor is almost constant, minus VO, with our small ripple approximation, and it will reach the same point at the end of this cycle, and this is going to repeat in every cycle. So the inductor current is going to be like a triangular waveform with certain average value. And what is the average value of this inductor current? As we know, the average value of capacitor current IC in periodic steady state is 0. So the average value of inductor current should be equal to the average value of IO. That means the average value of inductor current is equal to VO average by R, that is nothing but VO by R. And what is the peak to peak value of inductor current? Delta IL. It can be obtained by looking at the slope of this rise. Since the rise is linear, we can write as delta IL by dTs is equal to Vin minus VO by L. And since the average value of output voltage VO is equal to dVin, we can further express this as Vin times d into 1 minus d into Ts by L, or VO times 1 minus d into Ts by L. And what is Ts? Ts is one switching time period, the time period in which there is one turn on and one turn off transition of one switch. Ts is also the inverse of switching frequency, that is 1 by FSW, where FSW denotes the switching frequency. So if you want to know the value of L that has to be used in a particular buck converter, you can specify the peak to peak ripple under certain operating conditions. For example, VO, we need this much output voltage, and this is the input voltage that is available. For a given input voltage available, this should be my duty ratio that can be obtained from the average output voltage requirement. Once we know the average output voltage requirement, if we specify the switching frequency, then we will get the, and also the peak to peak ripple in inductor current, we will get the value of L. Here an interesting point to note is, as switching frequency increases, the value of inductance decreases for a given peak to peak ripple. So you can get the same peak to peak ripple with a smaller inductance if you increase the switching frequency. But the switching frequency is again limited by the device properties. Some switches can switch very fast, whereas the others cannot. Having known the inductor current waveform, we can easily plot the capacitor current waveform. Why do you want capacitor current waveform? Because we want to plot the output voltage waveform. So the capacitor current waveform is nothing but, the capacitor current expression is nothing but IL minus VO by R according to the KCL that we have written earlier. So it is just a subtraction of VO by R from IL. Since VO is almost constant, it will be a shifted version of IL with an average value 0, and that is obvious because the average current of the capacitor should be 0 in periodic steady state. That is what is depicted here. So the areas under the positive portion and negative portion of this capacitor current waveform are the same, and the peak value of capacitor current is delta IL by 2 as shown here. Now that we know the capacitor current waveform, we can easily plot the output voltage waveform, which is the capacitor voltage, and that is nothing but the integral of capacitor current. And again, integral, where will it start? It will start from the initial condition. If you assume that we start at one point, it will fall, and the fall will follow a kind of parabolic function because the capacitor current is going to have linear and it is negative to start with, and then subsequently the capacitor current becomes positive and it stays positive. That means dV by dt is positive, so the voltage is going to rise, and again the voltage will fall and it will go on. The average value of output voltage is denoted by VO, and as we have derived, it is going to be equal to d times V in, and the peak to peak value of output voltage delta VO, which is denoted here, and that needs to be determined now. And we need to make sure that this delta VO is much smaller than VO, the average value, because that is the basis of this whole analysis.